Hey guys, welcome to topic 2.2 water. But first, let's review the last little bit of 2.1 before we move on. So, understanding number 5 in topic 2.1 is about anabolism. Anabolism is the synthesis of complex molecules from simpler molecules, including the formation of macromolecules from monomers by condensation reactions. Okay, that's a mouthful. Really, all that means is that anabolic reactions, these are how you build bigger molecules. Think about anabolic steroids. People take them to build muscle mass. They're building bigger molecules from smaller molecules. So you'll see these anabolic reactions called a couple of different things. They can be called condensation reactions because they produce water. You'll also see them called dehydration synthesis. And again, dehydration because you're going to remove water, and synthesis because you're creating a larger compound. Now, anabolic reactions require the use of energy to build polymers from monomers. Well, that makes sense, right? Because remember, energy is stored in chemical bonds. So, in order to build polymers, poly meaning many, mono meaning one, you're going to link them together with bonds, and in those bonds is stored energy. Remember, energy is stored in bonds. Okay. And like I said, we remove a water molecule in this process. So let's take a look. Here we have a carbohydrate monomer, C6H12O6. Okay, well, that's a 1-to-1 ratio of carbon, hydrogen, and oxygen. So I immediately know that it's a carbohydrate. I can also tell from this ringed carbohydrate structure. It's got 6 sides, so it could be glucose. We're going to add another. Oh, this one's got 5 sides. So it's not glucose. Maybe it's ribose. Not sure. It could be fructose. But you can see we have a hydroxyl group here and a hydroxyl group here. And you'll notice that I have them a different color. They're red, right? That's because a bond is going to form between this carbon and this oxygen. And we're going to link these two monomers together. So let's see that happen. And there's our water that came out. That is why we call it a dehydration synthesis. We made a bigger molecule, we made a disaccharide, a polymer, by putting two monomers together. Now, the reverse of that is a catabolic reaction. Catabolism is the breakdown of complex molecules into simpler molecules, including the hydrolysis of macromolecules into monomers. This is understanding number 6. And I always remember it this way. We talked about how like anabolic is like building things up, right? Catabolic is breaking things down. Like, you know how cats always like knock stuff off the counter and break stuff? Catabolic, you're breaking it down. Now, we're going to add that water back in to break this molecule apart. This process is also called, wait, I don't want to do it yet. I'm trying to like write on my screen. Hydrolysis. Remember this from freshman year? Hydro means water, and lysis means to break, right? So we're breaking stuff with water. So here we have our disaccharide, right? We've got one monomer over here, our second monomer over here. That's why it's a di, because di means two, right? We're going to add some water to it. There's our water. And we split those molecules apart. Exactly like anabolism, but backwards. So, in review, in anabolic reactions, this is building, right? You're going to consume energy because it's stored in the bonds that link the monomers together. Right? That's that covalent bond. It's stored in that covalent bond. So energy is consumed because it's stored in the covalent bond. Water is going to be removed. And remember, you're building, right? Monomer means one. It's a polymer, which is more than one. So you're building a bigger molecule. Conversely, catabolic, hydrolysis, you're breaking things down. Right? Energy is released because you're breaking that bond. So the bond is broken, and that's what's going to release energy. So think of things like cellular respiration, right? You're breaking glucose down and you're releasing that energy. You do this by adding water, and you're turning those bigger molecules into smaller molecules. And so if you think about it, if cell respiration is breaking, right, you're breaking glucose and you're creating ATP. Well, yeah. Photosynthesis is the opposite, right? This is when you're building glucose and storing energy. So, anabolic, building bigger molecules, catabolic, breaking molecules back down. Okay, so now that we've gone over that one more time, at this point, you should be able to do a couple of different things, and hopefully, I'll have your quizzes graded. So, last quiz, I asked you to define molecular biology. You should be able to list the 4 major classes of biomolecules or macromolecules. You should be able to define metabolism, right? Which is the combination of all anabolic and catabolic reactions in the body. You should be able to outline the differences between anabolism and catabolism, and you should be able to identify or draw simple diagrams of a couple of different basic organic molecules, like glucose with 6 sides, ribose with 5 sides, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Fatty acids, those long chains, right? Sometimes you see them like that. Sometimes, anytime you have like super long chain, right? You get that. And then your amino acid, which is the butterfly. You've got that central carbon, you've got a hydrogen, you've got a carboxyl group, you've got your amine group, and then you've got your R. Wow, my handwriting is super horrible. It doesn't help that the screen is like up, not flat. Okay, so that was review. Let's move on now, finally, to topic 2.2, water. And again, this is a review of stuff that you learned freshman year. We learned about all those special properties of water that make it awesome. And it's the reason, like, if we're looking for life on other planets, the first thing we look for is water, because life as we currently define it and as we currently know it depends on water because it's special. Okay, so water molecules. Understanding number 1. Water molecules are polar and hydrogen bonds form between them. So, water molecules have 1 oxygen, which has 6 valence electrons, and 2 hydrogen, which has 1 valence electron, right? So, the hydrogen is like the Mickey Mouse ears, and they're positively charged, and the oxygen is like the Mickey Mouse head, and it's negatively charged, right? As a result, you've got an unequal distribution of charges. The top of Mickey's head is more positive than the bottom of Mickey's head because the bottom of his head is oxygen, right? So his ears are positive and his face is negative. That unequal distribution of charges makes a molecule polar. So when we talk about polar, that's what we're talking about. One side positive, one side negative. Sometimes you'll see that called dipolarity. Di meaning two, polarity meaning poles. It has two poles. Not bipolar, dipolar. So when water molecules get close, hydrogen bonds form between them. Hydrogen bonds are unique. They're like the side chicks of chemical bonding. So, in chemistry last year, you learned about covalent bonding and ionic bonding, and you probably learned about um, metallic bonding. Hydrogen bonding isn't like any of those. So, this is kind of like a PG 14 way of thinking about it, but you can think of chemical bonding as kind of like relationships, right? So, like you have covalent bonds, and covalent bonds are when two molecules are like sister wives, they share electrons equally, right? Then there's ionic bonds. An ionic bond between two atoms is like a home wrecker, right? Like one atom moves in and like steals completely the electron from the other, like stealing your man. That molecule just came in and stole your man. That's an ionic bond. Then there is metallic bonds, and that's kind of like swingers where the molecules just, or the electrons just jump from atom to atom to atom, and we're not really going to talk about that. Hydrogen bonds are different. They're not like any of those things. Hydrogen bonds are temporary and they're weak. They're kind of like side chicks or like having like a sly crush on somebody. Like you're still with the person you're with, right? But maybe you want to be talking to somebody else. That is a hydrogen bond. It's temporary and it's ephemeral. So, hydrogen bonds result from the attraction between the positive hydrogen and the negative oxygen of different molecules. So, here we have a diagram. Here's one Mickey head, right? And here's another Mickey head. So, if you just look at those two, right, the hydrogen bond is this hydrogen being attracted to this oxygen. So it's the hydrogen from one molecule to the oxygen of another. Similarly, you have this hydrogen, right, who is attracted to that oxygen. So it's hydrogen and oxygen attraction between different water molecules. Side chicks. And just like most kind of like side chick relationships or side piece relationships, those bonds tend to be a little bit weaker than the covalent bonds that are holding the water molecule together. Okay, understanding number 2. Hydrogen bonding and dipolarity explain the cohesive, adhesive, thermal, and solvent properties of water. So, freshman year, you guys did posters on this. When we talk about cohesion, we're talking about the fact that water molecules are sticky, right? So everybody's like, is water wet? No, water's not actually wet. Water is sticky. Water molecules stick together because of that hydrogen bonding. And that makes sense. So you ever try to like put your jeans on while you're still wet and like it sticks to your body? It's just not a good thing, right? So that's because water molecules are sticky. Hydrogen bonds between water molecules result in water being cohesive, meaning water sticks to itself. I think freshman year I had you guys like hold hands and then everybody pulled everybody, right? That same property is what gives water surface tension. So in the picture, you can see a water skeeter or a water skater that's skating on top of the water. Now, that small insect can actually skate on top of the water because it's so light that the hydrogen bonds between the water molecules, those temporary hydrogen bonds, are enough to support the weight of that insect, right? So it's not actually breaking surface tension. You can think of it as like, when you fill your glass up with water like way too much and it really should be spilling, like you can see the bubble on top. It looks like water should be spilling over the edge, but it's not spilling yet. But if you touch it, it's going to spill, right? That's surface tension. It's the surface tension that's keeping those water molecules together. Now, cohesion is super important for plants, right? Plants use cohesion to transport water from the roots through the stems and out of the leaves, otherwise known as transpiration. And remember, this process is why we have lots of humidity in the air. This is a really important process for our climate, and it's also super important for plants. That's how they get water up to their leaves, for photosynthesis so that they can give us oxygen that we breathe. Bringing it full circle because plants are awesome. As molecules move up through the tissue, those hydrogen bonds cause them to pull the water molecule behind it. So sometimes you'll hear this called capillary action. Like if you make tea at all and you have like a tea bag with a string on it and you leave the tea bag in there, the water will creep up or the tea will creep up the string and then like pool on the outside. That's capillary action because as one molecule of water moves up, it pulls the one behind it. Like when you're holding your friend's hand and you're trying to like walk through a crowd and you pull them behind you, that's cohesion. Now, water molecules don't just stick to each other, they stick to other things, right? And that's because of dipolarity. So, adhesion is what causes water to stick to the sides of a graduated cylinder. You have that meniscus, right? You guys probably learned about this a long time ago. You have the meniscus where the water kind of creeps up the sides. Whenever you're measuring water, you have to measure it at the lowest point, right? Not the top, not up here. It's because water molecules stick to stuff. Water is sticky. It's this adhesion property that allows plants to transport water in columns against gravity, right? So cohesion is what pulls water molecules behind it, but you got to remember trees are pretty tall and like they don't have muscles and stuff. So transporting water against gravity is kind of tough. It's this adhesive property of water that lets water be transported high against the force of gravity. The next property of water that we're going to talk about is thermal or specific heat, right? So hydrogen bonding provides water a high melting point and a high boiling point. And this is super important for a couple of different reasons. Here in this diagram, you can see that there's hydrogen bonding between the water molecules, right? Temperature is related to the rate at which molecules vibrate. So as we add energy, those vibrations increase and the temperature of the fluid increases. However, hydrogen bonds hold the water molecules together for a little bit longer than normal. So it slows that vibration. That's why it takes water so long to boil, right? You've got to add water, or you've got to add heat to the water to get those molecules to vibrate. But then on top of it, these hydrogen bonds, they're not about that life. So they're going to like resist that vibration. So you need even more heat to actually get water to boil. Now, this works in our favor for a couple of different reasons, but I'm going to let you figure that out in our in class activities. The end result is that you need more energy than is typically necessary to increase the temperature of bodies of water. When we talk about specific heat, we're talking about the energy required to increase 1 gram of that material by 1 degree centigrade. So water specific heat is 4.18 joules per gram per centigrade, which is higher than most materials. If you look at the table, you can see you've got water in the different phases here, right? And then you've got other materials down here. So liquid water, it takes literally twice as much energy to heat liquid water 1 degree compared to solid ice, right? So it literally takes more energy to boil water than it does to melt ice. Likewise, it takes twice as much energy to increase the temperature of water as it does water vapor. It takes a lot more energy to heat up water than it does dry air. That's really important when you start thinking about our atmosphere and thinking about our oceans in particular. Our oceans sit outside in the sun all day, and so does our atmosphere. And they both absorb heat that's re-radiating from the earth after being absorbed, right? That's the greenhouse effect. And our oceans absorb a ton of heat, 4 times as much heat as the air does. And then you can see we have some rocks down here, right? It doesn't take very much energy at all to heat them up. Think about walking through that hot sand at the beach, right? Doesn't take a lot of energy to make that stuff hot. So, water's high specific heat helps us maintain a stable environment for both marine organisms and terrestrial organisms, right? So, air temperatures change pretty quickly. The sun's out, it's hot. The sun's not out, it's not hot. However, water takes a lot of time and a lot of energy to heat up, but it also releases that heat much more slowly. So, as much energy as it takes, it also doles it out much more slowly. You can see in this diagram, this is water temperature over a year. Now, because that water acts like a battery, it sucks up heat all day long and it releases it slowly at night. Likewise, it absorbs a lot of heat during warmer months, depending on what hemisphere you're in, and releases it through currents slowly, mitigating big extremes in our climate. Because of hydrogen bonds, water also has a high latent heat of vaporization, right? So that means the amount of heat it takes, right, to turn liquid into gas. So, one way to analyze these special properties is to compare water to other common organic compounds. So, if we compare the thermal properties of water with those of methane, and remember, methane, it's an organic molecule, CH4, right? Also known as farts or burps. Here we have methane on the left, and we have water on the right. So, methane is nonpolar, whereas water is polar. It has that unequal distribution of charges, right? It's positive here and it's negative there. The specific heat of methane is 2.2, whereas water, it's 2.8. That means it literally takes twice as much energy to heat up methane. Oh, wait, no, my bad. It takes twice as much energy to heat up water compared to methane. Or I guess you could say it takes half as much energy to heat up methane as it does water. Then you have the latent heat of vaporization, meaning it does not take very much energy at all to cause methane to evaporate, whereas it takes quite a bit of energy to make water evaporate. Likewise, it doesn't take much energy to make methane boil, which is kind of like these are the same thing, right? They kind of mean the same thing. They are the same thing. I think of them as the same thing. Latent heat of vaporization. How much heat does it take to make something go from a liquid to a gas? That's latent heat of vaporization. And then we have boiling point. Wait a second. That's not right. Boiling point is what. Are these switched? I think these are switched. Yeah. Either way, you get the idea, right? Lots of energy to heat up water, not so much methane. This is exactly why we sweat water, right? I mean, there's other stuff in there too. But water's high latent heat of vaporization allows organisms to use it as a coolant. So when you sweat, right, that water is sitting on top of your skin. That water molecule absorbs heat until it evaporates. And as it evaporates, the energy is carried away and the body is cooled. Now, think of it this way. We said, say we sweat methane instead, right? That methane would only be able to absorb about half the energy that water does before it evaporated. So you'd have to sweat twice as much, right? But because we sweat water, it absorbs twice the amount of heat from your body before it's evaporated and carried away. So you get twice the cooling. The next property of water that we'll talk about is the fact that water is a solvent, right? That polarity helps water molecules physically pull apart other molecules. So here we have a big cube of sodium chloride, right? The green is the chloride, and the red is the sodium. Now, because water molecules have that unequal distribution of charges, they can use those charges to physically pull individual ions away from a solid. This is why sugar and salt and other things dissolve in water. Now, that becomes really useful if you're a living organism, right? Glucose is soluble and it flows through water in your blood. It's carried and dissolved by water in your blood. So, this is application number 3. Modes of transport of glucose, amino acids, cholesterol, fats, oxygen, and sodium chloride in the blood in relation to their solubility in water. So, because of water's solvent properties, organisms use water as a medium for reactions. Think about in the cytoplasm, right, where cellular respiration is going on. Or if you're a plant, photosynthesis. Actually, no, that's not in the cytoplasm. That's in the chloroplast. My bad. Let's go back to animals for a minute, right? We use water as a medium to transport things. So, your blood, a large component of your blood is water. Not all of it, right? There's plasma, there's red blood cells, there's white blood cells, there's other stuff. But really, by volume, a lot of it's water. You're 70% water, and that's for a reason. That's because certain molecules are dissolvable in water, and it's really easy to transport them around your body. Glucose is a polar molecule, meaning it has an unequal distribution of charges, and so it's hydrophilic. It freely dissolves in blood and is easily transported throughout the body. That's your blood sugar, right? How much glucose do you have in your blood? Sodium chloride is an ionic compound and it disassociates into that sodium and chloride ion in the blood plasma and then can move around your body freely. Now, we'll talk more about amino acids soon, but just as a refresher, remember your amino acids are that butterfly, right? And there are 20 different amino acids, there's 20 types, and the only thing that's different about them is the R group, right? So I'm going to draw it over here in the corner. You have that central carbon, you have your carboxyl group, you have your amine group, right? And you have your there's a hydrogen down here. It's not letting me do it. Here, let me get rid of the captions for a minute. So I have more space. Not going to let me do it? It's not going to let me do it. We have our R group, and then you have your central carbon, carboxyl group, amine group, and then down here, there's another hydrogen. Anyways, we're talking about the R group. The R group is different for each of the 20 different types of amino acids, right? It's this R group that determines how soluble an amino acid is. All of them are soluble, but some are a little more hydrophilic or hydrophobic than others. So some are transported easily in the blood, some not so much. Now, oxygen is an interesting one. Oxygen is nonpolar. Even though when it's by itself, it has negative charge. It usually bonds together to become a stable compound. So it's not polar. It doesn't dissolve very efficiently. So in order to meet the needs of cell respiration, your hemoglobin has to have a iron molecule in the middle so that that oxygen can bind to it, right? So oxygen doesn't dissolve because it's nonpolar, so not so great at flowing through blood by itself. That's why you have an entire protein called hemoglobin devoted to transporting oxygen because it doesn't dissolve readily in your blood. Fats or lipids are large molecules. Cholesterol is small, but they're both nonpolar, which makes them insoluble. They are not soluble in water. And that makes sense, right? Like when you put olive oil in a pot of boiling water for your spaghetti, it like bluebles at the top and like doesn't mix, right? Yes, blueball is a technical term. Not really, but you know what I mean. When like a drop of oil or fat floats on top of water, that's because it's insoluble. So instead, your body has to uh, transport fats and lipids in vesicles instead, in little membrane balls that are made out of the same stuff. So instead of dissolving, they're carried in lipoprotein complexes or vesicles, like literal fat sacks. That's actually what they are. And these complexes are surrounded by a single layer of phospholipids, right? Because remember, your phospholipids, the heads are hydrophilic, so they like water, and then the inside is hydrophobic. So all your hydrophobic fat molecules go on the inside, and then you have these little vesicles of fat that travel through your body because they don't like water. Okay, so let's review. We talked about different properties of water and what their function is. So we said, and I think remember the most important thing is these properties are primarily the results of hydrogen bonding and polarity, right? So it's those two causes that result in these properties, and these properties have very important functions when we're talking about life, right? So cohesion allows for certain organisms to walk on water, and capillary action, which is the combination of cohesion and adhesion, allows plants to transport water for transpiration. Water is a good reaction medium, meaning lots of substances dissolve in water, so it makes a appropriate place for different chemical reactions to happen. Think about all those aqueous solutions that you talked about in chemistry. Because lots of substances dissolve in water, that makes water an excellent medium to transport these substances in the fluids of living organisms. Additionally, water is super great at maintaining temperature or mitigating temperature, whether it's holding on to heat, right? Or helping heat escape. So, high specific heat creates a stable environment both internally and externally for organisms. Evaporation of water, sweating, panting, and transpiration helps cool organisms down. And then we have water as a solvent. Polarity allows water to dissolve other polar or ionic compounds, and that feeds right into transport, like we said. Okay, understanding number 3. Substances can be hydrophilic or hydrophobic. Remember, water is polar and it forms hydrogen bonds with other molecules. And you can see this. This is a video of lipids self organizing to form a cell membrane in water. So the green molecules are the fatty acid tails of phospholipids, and you can see the blue and red dots are the hydrophilic heads, and then the little gray molecules that you see, that's water. So, because phospholipids have that hydrophilic head and that hydrophobic tail, those tails point inward, trying to escape the water, and the heads point outwards. This self organization of chemistry is what helped lead to the origination of life on our planet. So, these properties of water, right, the fact that they can form these hydrogen bonds, and the fact that fatty acids are not polar and they have an aversion to water causes them to self-organize. That in turn forms a protocell membrane, right? That protocell membrane becomes a cell membrane later on. I know I'm jumping all over the place, but like I just can't impart to you enough how important these underlying foundational principles are, right? Without water, this doesn't happen. So, just to review, hydrophilic means water loving. Substances are polar and that are attracted to water that allows them to dissolve. Meanwhile, hydrophobic, water fearing, they're not polar, they do not form hydrogen bonds, and they're insoluble. So you can see in this diagram, we have all this hydrophobic tails pointing in, and we have the hydrophilic heads pointing out, and we have water on the outside, right? And there you have the self-organization of something like a cell membrane. Pretty neat. Just as a review, phospholipid structure, right? We just talked about that. Here's your glycerol head, which is hydrophilic. And then you have the fatty acid tail, which is phobic, right? Hydrophobic. And this is how we get the cell membrane. And we'll talk all about that later when we get into topic 2. And that is the end of the show for today. So, I look forward to seeing you guys in class tomorrow. We're going to look at some real life data and decide what is evidence and what isn't about the thermal properties of water and why it's important for life. And I look forward to seeing you then. Peace.